Welcome! Today, we'll tackle the problem delete characters to make fancy string, number 1957. This is an interesting string manipulation challenge where the goal is to ensure no three consecutive characters in the string are the same. Let's dive into the details and explore the solution step by step. In this problem, we are tasked with transforming a given string S into what is called a fancy string. A fancy string is defined as a string where no three consecutive characters are the same. To achieve this, we need to delete the minimum number of characters from the input string S so that it satisfies this condition. Once the modifications are complete, the resulting string should be returned as the output. The input string S consists of only lowercase English letters, and its length can range from 1 to 100,000. This means we need to ensure our solution is efficient enough to handle large inputs within these constraints. Let's look at the first example to understand the problem better. The input string is S equals LeetCode. In this case, the string contains 3 consecutive E characters. To make the string fancy, we delete one of the E characters. This gives us the resulting string LeetCode, which satisfies the condition because no 3 consecutive characters are the same. This is the minimum number of deletions needed, so the output is LeetCode. Now, consider the second example with S equals Aabaya. In the second example, the input string Aabaya has groups of 3 consecutive characters both at the start and in the middle. To make this string fancy, we need to delete one from each group of 3. After performing these deletions, the resulting string is Aba, which is now fancy because it no longer contains 3 consecutive identical characters. This output satisfies the condition with the minimum number of deletions. Now let's take a look at the third example, where the input is S equals Ab. Here, the input string is Ab. This string already satisfies the condition of being a fancy string because it does not contain any group of 3 consecutive identical characters. Since no deletions are necessary, the output is simply the input string itself, which is Ab. With this example, we can see that if the input string is already fancy, no changes are required. Let's now consider some constraints and edge cases that may arise when solving this problem. The constraints specify that the input string S will always have a length between 1 and 100,000, and it will only consist of lowercase English letters. For edge cases, consider a string with a single character, such as S equals A. This string is automatically fancy because it doesn't have enough characters to form 3 consecutive identical ones, so the output is A. Another scenario is when the string is already fancy, such as S equals apkapkap, where no deletions are needed, and the output remains the same. Finally, for a string with all identical characters like S equals AAAA, the minimum fancy string would retain only the first 2 characters, resulting in AA. These examples highlight the different scenarios we need to handle while solving this problem. To tackle the problem of transforming a string into a fancy string, we explored several approaches. The first method considered is the brute force approach. The intuition here is straightforward: we scan the string and remove characters whenever 3 consecutive identical ones are found. This process is repeated until no violations remain. The steps involve traversing the string character by character, identifying sequences of 3 identical characters, and removing the third character in such cases. Each removal requires restarting the traversal until the string satisfies the condition. However, the downside of this approach lies in its inefficiency. The repeated scanning leads to a time complexity of O(n squared), as we may need to process the string multiple times, and the mutable string itself requires O(n) space to handle. While simple, this method is not scalable for large inputs. The inefficiency of the brute force approach prompted us to consider a more optimized solution using a 2-pointer traversal. This method eliminates the need for repeated scans by constructing the result string dynamically in a single pass. The key insight is that we only need to check the last 2 characters of the result string to ensure no 3 consecutive characters are the same. The steps involve creating an empty result list, traversing the input string character by character, and appending each character to the result list if it doesn't form 3 consecutive identical characters. Otherwise, the character is skipped. Finally, the result list is converted back to a string and returned. This approach is highly efficient, with a time complexity of O(n) due to the single traversal of the input string, and a space complexity of O(n) for storing the result list. It is both elegant and practical for handling larger strings. The optimized approach offers significant advantages, making it a strong candidate for solving this problem. Its efficiency stems from avoiding redundant traversals and focusing on the immediate local context. Another approach we explored is the recursive solution. Here, the problem is addressed by processing the string character by character and handling violations recursively. If 3 consecutive characters are detected, the third character is skipped, and the remaining string is processed further through recursive calls. While recursion provides an alternative perspective, it introduces overhead due to the recursion stack. The time complexity can remain O(n) in the best case, but the stack space usage makes it less practical compared to the iterative solution. Recursion is generally not ideal for a problem like this, where an iterative solution is more straightforward and avoids unnecessary complexity. After evaluating the different approaches, we selected the optimized two-pointer traversal strategy as the best solution. This method stands out for its linear time complexity and efficient memory usage. The key insight driving this approach is that checking only the last 2 characters of the result string at each step is sufficient to ensure no 3 consecutive identical characters. This simplifies the problem, avoiding redundant checks or unnecessary recursion. 2 important observations solidify this choice: first, that local context suffices to maintain the required condition, and second, that constructing the result string dynamically allows us to achieve the solution in a single traversal. The trade-offs are clear. While the brute force approach is easy to understand, it is computationally expensive. Similarly, the recursive solution, though effective in theory, adds unnecessary overhead. The optimized solution achieves the perfect balance between simplicity and efficiency. The optimized approach is the ideal solution for transforming a string into a fancy string. It balances simplicity and efficiency, leveraging a single traversal and minimal space usage to solve the problem effectively. By focusing only on the immediate local context of the last 2 characters, it ensures correctness without redundant computations. This method exemplifies how a clear understanding of the problem and its constraints can lead to an elegant and scalable solution. For this reason, it is the strategy we recommend for tackling this problem. In this problem, we are tasked with transforming a given string into what's called a fancy string. A fancy string is defined as one where no 3 consecutive characters are the same, and our goal is to preserve as much of the original string as possible while ensuring this condition is met. To achieve this, we start by initializing an empty string called result, which will store the transformed output as we process the input. This allows us to build the fancy string step by step. Next, we iterate through each character in the input string using a loop. During each iteration, we check the last 2 characters already added to result if they exist and determine whether adding the current character would result in 3 consecutive identical characters. If it does, we skip the current character. Otherwise, we append it to result, ensuring the condition is satisfied at every step. The process continues for every character in the input string, systematically ensuring that no 3 consecutive characters in result are identical. By the time the loop completes, the result string will meet the condition of being a fancy string. Finally, we return this result string as our output. This ensures that the transformed string is not only valid but also retains as much of the original character order as possible, fulfilling the requirements of the problem. This algorithm is efficient because it processes each character exactly once, making it an O(n) solution, where n is the length of the input string. Each step involves a constant time check to compare the last 2 characters in result with the current character. The approach is also greedy, meaning that decisions are made locally at each step based on the immediate condition of avoiding 3 consecutive identical characters. This ensures the original order of characters is preserved as much as possible. Additionally, the algorithm handles edge cases gracefully. For example, if the input string is empty, the output will also be empty. For strings with fewer than 3 characters, no transformations are needed, so the input can be returned as is. Strings with repetitive patterns, such as AAA or ABABAB, are adjusted by skipping specific characters to meet the fancy string condition. The solution uses only a single string, result, to store the output, and no additional data structures like stacks or queues are required, making it both simple and memory efficient. Let's look at an example to see how the algorithm works. Consider the input string ABABA. We start with an empty result string. First, we add the character a, resulting in result equals a. Next, we add another a, giving us result equals a. When we encounter the third a, we notice that the last two characters in result are already a, so we skip this character to avoid forming three consecutive a's. Moving on, we add the character b, which updates result to ob. The next two characters, a and a, are added sequentially, resulting in result equals aba. When we reach the final a, the last two characters are again a, so this character is skipped. The final output for this input is aba. For a simpler input like ABCD, we add each character directly since no three consecutive characters are identical. The output remains ABCD, unchanged from the input. The key operations in this algorithm involve comparing characters and appending them to the result string. Checking the last two characters in result is a constant-time operation, as Python strings allow efficient index-based access. Appending characters to the string is also efficient, ensuring smooth performance. For optimizations, we could consider modifying the input string in place for environments where strings are mutable, reducing memory overhead. Additionally, we can short-circuit the algorithm for strings with fewer than 3 characters, returning them early without processing. For scenarios involving high-volume input, processing strings in batches could further optimize memory usage. In terms of complexity, the time complexity is O(n), since each character is processed exactly once, and the space complexity is also O(n), as we store the transformed string. This balance of simplicity, efficiency, and correctness makes the algorithm well-suited for large inputs and diverse cases. The implementation of the solution for LeetCode problem number 1957, delete characters to make fancy string, begins by defining a function makeFancyString within a class solution. This function takes a single input string s. We initialize an empty list result to store characters of the transformed string. Using a list instead of a string for intermediate storage is efficient because string concatenation in Python is costly due to immutability, whereas appending to a list is faster. Next, we iterate over each character in the input string s. For each character, we check whether adding it to result would cause 3 consecutive identical characters. This is done by verifying if the length of result is at least 2, to avoid out-of-bounds indexing, and if the last 2 characters in result are the same as the current character. If these conditions are met, we skip adding the character to result. If the conditions are not met, i.e., adding the character does not violate the fancy string condition, we append the current character to the result list. After the loop completes, we use the join method to convert the result list back into a string and return it. This produces the transformed fancy string that satisfies the condition of having no 3 consecutive identical characters. This implementation efficiently handles the problem's requirements with a time complexity of O(n), where n is the length of the input string, since we traverse the string once. The space complexity is O(n) as well, due to the storage of characters in the result list. This is the Java implementation of the delete characters to make fancy string problem, LeetCode number 1957. The logic mirrors the Python implementation, using a string builder instead of a list for efficient string construction. The method iterates through the input string, appending characters to the result only if they do not form 3 consecutive duplicates. Java-specific features, such as the char@, method in string builder, are utilized to ensure optimal performance. To solve the problem, we'll iterate through the string while maintaining a result list to build our fancy string step by step. Starting with the input s equals a, we initialize result as an empty list. The first character is a, and since result has fewer than 2 characters, we add it to result, making it a. Next, we process the second character, also a. Again, because result has fewer than 2 characters, we append it, giving us a. Now, the third character is another a. This time, the last 2 characters in result are both a, so we skip this character to avoid 3 consecutive a's. The result list stays as a. Moving to the fourth character, which is b, the last 2 characters in result are not both b, so we add b, and result becomes a b. For the fifth character, the last 2 characters are not both a, so we add a, resulting in a b. Continuing with the input s equals a, we now process the sixth character, which is a. Since the last 2 characters in result are not both a, we append a, making result equal to a b. For the seventh character, another a, the last two characters in result are both a, so we skip this character. The result list remains a, b, a. Finally, we process the eighth character, a, and again, because the last two characters are both a, we skip it. The result list is now finalized as a, b, a. Converting this list back to a string gives the final output, a, b. Now let's consider another example with a simpler input, s equals abc. To start, we initialize an empty result list. The first character is a, and since result has fewer than two characters, we add a, making result equal to a. Next, the second character is b. The last two characters in result are not both b, so we append b, resulting in a, b. Finally, the third character is c. Again, the last two characters are not both c, so we add c to the list. At this point, result is a, b, c. Converting this list to a string, the final output is abc. In this example, we'll analyze the input s equals a. We begin with an empty result list. The first character is added to result since the list has fewer than two characters, making it a. The second character, also a, is appended as well, resulting in a. The third character is again a. However, the last two characters in result are both a, so we skip this character. The result list remains a. The fourth character is another a, and since the last two characters are still both a, we skip this one as well. Similarly, the fifth character is skipped for the same reason. The final result list remains a. After processing all characters in the input string s equals a, we convert the result list back to a string. The final output is a. This demonstrates how the algorithm effectively limits consecutive characters to a maximum of 2, even when the input string contains repeated sequences. The time complexity of this solution is O(n), where n is the length of the input string. This is because the algorithm iterates through each character in the string exactly once using a for loop. Each iteration performs three main operations: evaluating a condition, accessing specific indices of the result list, and appending characters to the list. Let's break this down further. First, the condition check, which ensures we don't add three consecutive identical characters, runs in constant time, O(1), since it involves simple list indexing and comparisons. Next, appending a character to the result list is an amortized O(1) operation. When combined, each iteration of the loop involves O(1) operations, and since the loop runs n times, the overall time complexity is O(n). This linear behavior makes the solution very efficient for processing the entire string in a single pass. Now, the total time complexity remains O(n), as we've established that each iteration of the loop performs O(1) operations. Shifting focus to space complexity, the algorithm also has an O(n) space complexity. This is primarily due to the result list, which stores the characters of the fancy string. In the worst-case scenario, where there are no three consecutive identical characters, all n characters from the input string are added to the result list. Additionally, the input string itself requires O(n) space, but this is not extra space created by the algorithm, it's just the input. Therefore, the dominant factor in space usage is the result list, which can grow linearly with the size of the input. Additionally, the algorithm uses a few temporary variables, such as char, to reference individual characters during the iteration. These variables require only O(1) space and do not contribute significantly to the overall space complexity. It's important to highlight that the result list remains the primary contributor to space usage, as it can grow up to the size of the input string in certain cases. Comparing this approach to a naive or brute force solution, which might involve repeatedly scanning and modifying the string, this solution is far more efficient. Brute force methods could easily result in time complexities of O(n squared, or worse due to multiple passes over the string. By building the result in one pass, this algorithm achieves a significant improvement in both time and space efficiency. Now let's analyze the best, average, and worst cases for this algorithm. In the best case, even if there are no three consecutive identical characters in the input string, the algorithm still processes every character once and appends it to the result list. This means the time complexity remains O(n), and the space complexity is still O(n). For the average case, where the input string has some 3 consecutive characters, the algorithm skips adding those characters but still evaluates every character, maintaining the same time and space complexity. Finally, in the worst case, if all characters are distinct or there are no 3 consecutive identical characters, the algorithm appends all n characters to the result list, resulting in time and space complexity. This consistent linear performance across all scenarios demonstrates the efficiency of the solution. By visiting each character exactly once and performing operations per character, the algorithm guarantees time complexity. The space complexity is dominated by the result list, which can grow to size n in the worst case. Overall, this solution is highly optimal and avoids the inefficiencies of brute force approaches, making it well suited for this problem. When working on this problem, there are a few common mistakes to watch out for. First, not handling edge cases properly, such as strings that are very short. For example, strings like A or AA already meet the condition of a fancy string, as they don't contain 3 consecutive identical characters. Trying to apply extra checks or logic to these cases can overcomplicate your solution unnecessarily. Another frequent mistake is removing or skipping characters in a greedy manner without fully considering how this impacts the rest of the string. For instance, if you transform ob into ob, you might still end up with a string that violates the condition unless further checks are done. Lastly, it's important to preserve the original order of characters in the string. If your solution involves rearranging characters, it won't meet the problem's constraints, and you'll end up with an invalid output. Always ensure that the relative order of characters remains intact. Now, let's look at some additional pitfalls. Inefficient iteration is a common issue. Some solutions use nested loops to check every possible substring of length 3. This results in an n squared time complexity, which is far from optimal when a single-pass solution can handle the task. Another mistake to watch for is off-by-one errors. These occur when you miscalculate indices while checking for 3 consecutive characters. For example, if your logic extends beyond the bounds of the string, it could lead to runtime errors. Similarly, misaligned indices could lead to incorrect comparisons and unintended behavior, especially when working with strings near boundary conditions. Paying close attention to your indexing will help you avoid these issues. To boost your performance in interviews, it's helpful to recognize that this problem is a variation of sliding window or two-pointer techniques. The key is to maintain a valid window as you iterate through the string. An optimal solution involves iterating over the string in one pass, appending valid characters directly to a result variable, which ensures time complexity. During interviews, it's important to clearly explain how you avoid 3 consecutive identical characters in your implementation. This clarity demonstrates your understanding of the problem and the reasoning behind your approach. Don't forget to address edge cases, such as strings with fewer than 3 characters or those with highly repetitive patterns like AAA. Showing that you've accounted for these scenarios can set you apart as a candidate. Additionally, this problem shares similarities with other LeetCode problems, like remove all adjacent duplicates in string or longest substring without repeating characters, so solving those can reinforce your skills. When thinking about alternative approaches, there are a few strategies to consider, each with its own trade-offs. The greedy approach involves iterating through the string and building the result character by character, ensuring no 3 consecutive characters are the same. This method is efficient, with time complexity and space, but it does require extra space to store the resulting string. Another option is in-place modification, where you adjust the string directly by skipping characters that violate the condition. This reduces space usage to 1, but requires careful handling of indices to avoid errors, which can make the implementation more complex. Lastly, there's the recursive solution, which processes the string by repeatedly removing violations. While it can be elegant and intuitive, its performance depends on the input. For highly repetitive strings, the complexity can degrade to n squared, making it less suitable for large-scale inputs. Each approach has its strengths, so it's important to choose the one that best aligns with the problem constraints and your specific needs. Great job! We've successfully solved the problem delete characters to make fancy string. Remember, string manipulation problems like this are common in interviews, so mastering them can give you an edge. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!